Here at the San Francisco Bay Naval Shipyard, workers prepare SeaLab III, a special habitat for ocean floor dwelling, to be used by the aquanauts of the Navy's most ambitious undersea experiment to date. Already used in SeaLab II, major modifications to the cylindrical habitat were the addition of 2 rooms to the ends of the central section and an anchor ballast tank which would allow the habitat to remain level on the sloping ocean floor. Once all systems had been successfully tested in the dry environment, a dry dock is flooded for the evaluation of submerged tests of safety, reliability, and performance needed for the life support of the men who would live and work in and out of SeaLab during the deep ocean experiment in the Pacific. By nightfall, SeaLab was almost completely submerged, enabling an aquanaut to exit from the diving station and check out his semi-closed breathing apparatus, or if man is to effectively explore his new frontier, he must have ample mobility. Primary objective of the SeaLab III program is to evaluate techniques and equipment being developed and to extend man's capabilities to the limits of the continental shelf. Essential to this capability is a deep diving system for eventual use by the fleet. The prototype of such a deep diving system was built into the support ship, Elk River. A vital part of this system is the PTC, or Personnel Transfer Capsule, a pressurized elevator needed to transport divers to and from the ocean floor. Dress rehearsal site for the evaluation of special tools and equipment used by the salvage and construction teams in their parts of the ocean floor program is held near Anacapa Island, California. Like a couple of ocean astronauts, the divers don special headgear that provides protection, two-way communications, and a breathing system for life support. At 600 feet, his breathing gas of helium and oxygen, in correct mixture, is supplied by an umbilical from the habitat. Fully dressed, the aquanaut must carry 140 pounds of equipment.
Man, get ready to go in now. Go.
Their first task on entering the water is to check out each other's life support system. The 60-day ocean floor program will consist of experiments in physiology, oceanography, construction, search recovery, use of marine mammals, and salvage. In this experiment, aquanauts use a zipper to adjust the amount of lift desired in a variable buoyancy lift system. Since salvage work demands heavy heaving and hauling, this portable crane can lessen their burden. Because the cold water is numbing and saps his energy, special tools such as this must be designed for the diver and are evaluated in the actual ocean environment. A diver tool test stand serves as a workbench where the performance of tools is actually tested. One of these is an explosive stud driver, using gunpowder as a source of energy to drive studs through 1-inch armor plate. A human factors expert notes the time needed to complete each task, comparing their reactions to other environments like outer space. A restraining belt is worn by the aquanaut since buoyed weightlessness complicates his work. He tends to turn along with the drill, and if he hammers something, the reaction pushes him away.
Put him in the water, you guys are. Who's going in first?
At the same time, members of the construction team were about to practice their part in the ocean floor program to build a 15-foot tall house on the sea bottom. Using special lift devices and equipment, they will assemble 3 large concentric iron rings into a dry storage and repair facility.
I'm at the control console. Okay. All right. Get ready to operate the winch. Okay, down on the winch. Down on the winch, all right. Outside this is low. The lower ring is lifting off the bottom. The ring is lifting off the bottom. Lower ring coming off the bottom. Hey, Larry. Topside, this is Red Diver. Could you turn the volume up between divers to diver? I'll give you some more volume, Blue. Thank you. Looking good, Larry. Just want to get a picture story. Now, Larry, okay, is the trolley line flat yet? Is the trolley line...
Techniques learned in this experiment can lead to construction of other, larger structures and will eventually be the forerunner of major industrial and research complexes on the continental shelves of the world. At Point Mugu, California, another part of the ocean floor program is in progress. 3 aquanauts are introduced to a sea lion named Gimpy. She is one of 5 marine mammals trained to assist man in his research in the depths. Each underwater mammal has its own talents. The sea lion can streak from the surface to 600 feet in less than 30 seconds. Homing on a portable buzzer, Gimpy is rewarded and patiently waits for the aquanaut to transfer a buoy from one part of her harness to another. This training helps the mammal accept tools, mail, and geological samples when she eventually acts as a messenger from the surface to the aquanauts below. Also in training is a porpoise named Tuffy. Porpoises are the brightest of the marine mammals, and Tuffy proved during the previous SeaLab II experiment that he could act like a seagoing St. Bernard, taking a life-saving line from a rescue team to a lost aquanaut. With all modifications completed, the habitat is placed on a barge and towed from the naval shipyard at San Francisco to its next stop, Long Beach, California. During its brief stay at the shipyard, the underwater capsule is loaded with all the special equipment needed to make a habitat a home. Personal items, consumables, towels, and dry provisions. Meanwhile, the surface support vessel Elk River was departing from the San Francisco Bay Naval Shipyard and heading to the experiment site, an ocean engineering range on the leeward side of San Clemente Island. Once positioned in a 5-point moor, the Elk River begins final testing of the deep diving system installed during its conversion. A large gantry crane lifts the pressurized elevator and moves it forward for lowering through the center well. The PTC must be closely controlled and monitored, for during the upcoming experiment, if the capsule loses its pressure, the aquanauts inside could suffer fatal explosive decompression. Use of these capsules allows quick, safe transfer of aquanauts to and from the ocean floor. Helium and oxygen flasks, mounted on the outside, contain the proper mixture of gases the diver breathes during transit and while making excursions from the PTC. Once saturated with this inert gas, the aquanaut cannot return to the surface. To do so would mean certain death. He moves from his dry capsule to the wet ocean surrounding it, able to come and go freely through an invisible curtain. No intermediate lock is required because the pressure within the PTC is the same as the surrounding water. The salvage ship, USNS Gear, tows the fully loaded habitat on the last leg of its journey from the shipyard at Long Beach. Arriving at the experiment site, it awaits offloading by the large floating crane, the Marine Boss. As the habitat is pushed to the offloading site, aquanauts make final preparations. Diver umbilicals are tied together and then wrapped securely around special storage racks near the diving station. Heavy wire slings are prepared for the Marine Boss lifting bridle. Now the large crane must lift more than 300 tons of ocean floor dwelling. The SeaLab, resembling a railroad tank car, is almost 70 feet long and is painted a bright yellow for underwater visibility. The conning tower gives access while on the surface. When submerged, SeaLab measures 50 feet from the top of the conning tower to the bottom of its central anchor clump. The special support barge has been pulled away and SeaLab is lowered into the ocean. Marine Boss has done its job, and the final countdown begins. The habitat is gently towed to its lowering position near the support ship Elk River. There it is moored for installation of the habitat umbilical and support equipment. Divers inspect the habitat as it rests in its moor. Cables and fittings are carefully checked. With down day approaching, aquanauts and support personnel complete final inspection of all deep diving system components. Inside a personnel transfer capsule, mated to its accompanying deck decompression chamber, an aquanaut checks the gas monitoring panel and communications with other elements of the system.
Monitor control, this is capsule 2 for communications check. Over.
Below him, similar tests are being made between the deck decompression chamber and the main control console, which is the nerve center for the exacting process of careful decompression needed to bring men back to surface pressure from their saturated dive.
Full control, main deck. Full control line. Yeah, peak.
Monitor control.
This CDC-2, we check out okay on internal lights.
The next morning, everything is in readiness for the lowering procedure. The helium barge is alongside, and the YSD-60 is hooked up and ready to lower. Flooding of a ballast tank beneath the conning tower is the first step for lowering the habitat. Now almost awash, divers secure the hatch of the conning tower, second of 3 ballast tanks. The upper 2 tanks provide 9,000 pounds of negative weight, allowing the unmanned SeaLab to begin its descent. The 3rd ballast tank is in the anchor clump and will be flooded as part of the habitat opening procedure once it is safely on the ocean floor. Divers enter the water while SeaLab is held at 25 feet. For a final visual check before the lowering continues. Pressure of the gas within the habitat is kept slightly greater than that of the surrounding ocean to prevent flooding. As the habitat is slowly lowered, personnel on the Westinghouse support ship Search Tide ready their dry submersible Deep Star for its first observation dive. Once in the water, she will descend to 600 feet, permitting her SeaLab passengers to observe the final stages of the lowering and actual touchdown.
Bottoms in sight.
Elk River, this is Deep Star. The lab, it appears that she's going to make a beautiful landing.
Combat is control. Go ahead and pan and tilt one time to a final position.
During the night, a remote-controlled camera system monitored the habitat, while closed-circuit television cameras provided a close watch on the pressure balance within SeaLab. Early the next morning, pressure begins to drop. Gas is somehow leaking from the habitat. Immediately, a conference is held. The only way to stop a leak is from inside. The decision is made to compress 4 of the 9 men more rapidly than planned, so the unbuttoning crew can get into the habitat ahead of schedule. The aquanauts are given the go-ahead.
Okay, I'd like to get all members of Team 1 over here. I got 3 in there, and you 4, that's 7.
Arriving at the deck decompression station, the 4 aquanauts discuss the unbuttoning procedure and receive their final instructions from the diving officer.
Okay, guys.
They enter the chamber for compression to 600 feet at the rate of 4 feet per minute. It will take 2½ hours for their bodies to be equal to the same pressure they will experience on the ocean floor.
Diving officer, make your deck 14 feet on air. All right. Got a deal.
The remaining 5 members of Team 1 enter the other chamber for the planned 15-hour saturation to depth and to undergo physiological baseline studies. In the interim, Deep Star is requested to make another descent to the seafloor to try and accurately locate the leak and report back. This information is given to the 4 aquanauts preparing to descend. Personnel in the main control console area ensure mixes of gas during saturation are correct and keep track of the pressure within the leaking habitat. The 5 men undergoing standard pressurization busy themselves reviewing their assigned tasks and discussing the problem facing their teammates in the other chamber. By late afternoon, pressure is equalized between the decompression chamber and its mated personnel transfer capsule. The last-minute details for the dive are completed. The 4 aquanauts check their pressurized elevator before entering for the long ride to the ocean floor. On the main deck of the support vessel, the gantry prepares to separate the capsule from the deck decompression chamber, for this is no practice dive. The seal on the hatch of the capsule must hold, as the aquanauts are living at the same ambient pressure as that of the ocean floor, almost 280 pounds per square inch, 19 times greater than at sea level. Carefully, the capsule is swung over the center well for the strenuous job of attaching the downhaul winch, which also serves as a platform for the aquanauts when they exit at 600 feet. Man's maximum working depth in the sea, until recently, was considered to be 380 feet for 30 minutes with hard hat diving equipment. The Mark II system is designed to more than double that depth. The capsule then transfers to handling davits used with the main strength power communications cable, which is the aquanaut's lifeline to the surface. As they descend slowly toward the habitat, the aquanauts report on their progress. Because of changes in resonance brought about by the helium in their synthetic atmosphere, their voices sound garbled and unearthly.
Keep us in more every 50 feet, see that? See that, guy? 200. 400. 450.
Arkansas, what are you?
The leaks in the habitat are visible to the aquanauts as they approach the ocean floor. Gas is escaping through penetration fittings in SeaLab's hull, and more gas must be pumped down from the surface to keep the habitat from flooding. With their elevator on the ocean floor, aquanauts Barth and Cannon hook up their umbilicals and head for the habitat. They must flood the anchor clump ballast tank, ensure the habitat is level, and release gas to blow out the skirt or area beneath the entrance to the diving station before opening the hatch. Ballast tank number 3 has been flooded, and the skirt has been blown. Topside personnel watch Bob Barth through closed-circuit TV. He should now be able to open the hatch, but is having trouble with his breathing and must hit a bypass on his rig to increase gas flow. Tired, cold, and breathing heavily, Barth decides to head back to the capsule. Barry Cannon had already returned. The capsule is hauled to the surface, and the aquanauts gratefully entered the warm decompression chamber. But the problem has not been solved. In the pre-dawn darkness of the following morning, the decision is made to send the men down on a second dive. The leakage is worse and must either be stopped or the experiment aborted. The aquanauts return to the personnel transfer capsule for a second journey to the 100-fathom depth. Barth and Cannon again head for the troubled habitat. The problem is apparent to them as they approach. The light helium-oxygen atmosphere of SeaLab is bubbling out into the sea. For a second time, Barth's attempt to enter the door of his underwater home is foiled. Water has seeped back under the diving station skirt, and the hatch won't budge. Cold and frustrated, Barth swims for a crowbar positioned nearby, which can assist him in forcing open the hatch. Returning, he sees his partner Barry Cannon in trouble on the ocean floor. Dropping the crowbar, he rushes to Barry's aid. Cannon is shaking. His mouthpiece has come loose, allowing his vital breathing gas to escape. Struggling with the now unconscious body of his friend, Barth carries Barry to the diving station ladder. Propping Barry up, Barth tries desperately to give him breathing gas through the buddy breather regulator carried for just such an emergency. Again he tries. Still again, he tries to force the mouthpiece with vital gas into Barry's mouth. Suddenly, Barth himself begins having trouble breathing. His ears ringing, he feels as though he is going to pass out. Clasping Barry, he heads for the capsule and help. but he and his teammates' heroic efforts were to prove futile. Barry Cannon was pronounced dead on arrival at the deck decompression chamber. Diving operations have been suspended, and the on-scene commander is faced with a real dilemma. How is he to get the habitat back to the surface? It is still leaking badly and has the added weight of 17 tons of seawater in ballast tank number 3. Aboard the YSD-60, engineers prepared to make modifications to the counterweight system in order to handle the additional 17 tons of weight. To do this, 20,000 pounds of additional weight is added to the counterweight, bringing its total to about 35,000 pounds. And the weaker points in the raising system are either bypassed or strengthened by on-the-spot bracing to prevent buckling. The crane boom and the midship pulley were bypassed by cutting the aft I-beam to permit the actual lift from this corner of the ship. With the lifting problem solved, the helium barge was running out of gas. The air compressors on the support vessel couldn't keep ahead of the leaks. An urgent call for help was sent to a submarine with powerful air compressors. The question was, could she arrive in time to help? By nightfall, the lift had begun, and the submarine Diodon had arrived to handle the pressure problem. When the habitat was at 100 feet, divers entered the water to blow the ballast from number 3 tank and to attach nylon lines to guide SeaLab into a clear area for surfacing. Crews took up slack on the guidelines while support divers manned small boats. Then, suddenly, gurgling and gushing, the habitat surged to the surface, safe after engineers gave her a 1,000 to 1 chance of ever getting off the bottom.
Recovery of the habitat under emergency conditions was a truly outstanding performance. It will, in due time, enable us to complete all of the goals of SeaLab III program. While the unfortunate accident stopped the experiment far short of the goal, we were able to learn a great deal from this initial major step. In particular, we identified several areas which require detailed investigation before we can consider the first 100 fathoms to have been mastered. We plan to go ahead with a series of special dives using this system, using the Mark II diving system, without the habitat in order to solve these problems and get some exact data. We will do this while the habitat is being modified and repaired from its short excursion into the depths, while it's being refurbished with a particular aim of making it resistant to the high-pressure helium and the low temperatures to which it's exposed. Actually, the SeaLab III experiment will mark a major milestone in our progress into the deep ocean. It must be recognized, however, that this is not the end. Both industry and the Navy must continue to seek the means of diving deeper and longer and in safety. These are goals to which Barry Cannon devoted his life. It's up to us to make them reality.